Hello everyone, in this video I will quickly show you how to measure the current voltage characteristics of the diodes, bipolar junction transistors with the help of HP4145 semiconductor parameter analyzer. Let's start with the simplest measurement setup. The diode. We will use a 1N4148 as an example. Test forward voltage versus current dependency, connect SMU1 to the diode anode and connect SMU3 to the diode cathode. I am using this test fixture, but you can use any DIY jig you have. Just keep in mind that without the GPIB-like cable and the original test fixture, the instrument's source voltage will be limited to 40 volts. So connect the diode first. The anode goes to the SMU1 and cathode or the minus goes to SMU3. So once the device is booted up, you need to press one channel definition. Next, you need to press General and load the predefined setup for measuring diodes. So on this page, you don't have to change anything actually. As you can see, SMU1 is already configured to source a variable voltage and measure the current, and SMU3 is configured to maintain a ground reference or zero potential. That's why it is constant here. And our SMU is set to source variable voltage, like this. But this setup is totally fine for diodes and we can press next. And this page is the most important page. First you need to set up the start and stop voltages. The start and stop voltages should cover the region where your diode becomes conductive and slightly beyond, like plus minus few volts. For low power diodes like 1N4148, this is typically between like 100 millivolts and 1 volt, so we will set the sweep accordingly, adding a small buffer at the both ends. So these default setups are perfectly fine for us, just like that. So the step voltage should be chosen in such a way so that the total number of points doesn't exceed 200, or otherwise the instrument will run out of memory. Compliance current should not exceed the diode's rated forward current from the data sheet. So in our case, 40 milliamps pretty fine, but we can set up 100. That is totally fine for us, and remember, this instrument cannot go beyond 100 milliamps anyway. No changes are needed for the COM potential. It should remain 0 volts, and the same goes for compliance. We just set the maximum current here. Then we need to press next. On this display configuration page, you can leave the chart display limits unchanged, because basically the device in this case transferred the previous settings to these scale limits. Press next and we can start the measuring. So the next step would be to press single measurement button. Now we can see that the device has done the measurements, and this is basically everything you need to know about how to measure low power diode on this device. Additionally, you can just press extended button, press marker, and then just use the marker knob to move the cursor. And this way we can investigate when our diode is actually starting to conduct the voltage. Also, you can see the error 80, you can safely ignore it because it means just that the device has run into its current limit, which is okay. So here is the example of the settings for a slightly different diode. Its VI curve is slightly tilted to the right, and for that we need to configure a slightly wider voltage ranges. So I have set 3 volts here as a stop voltage, and same for the maximum voltage on the graphic. Let's press next and do the measurements. Let's do the measurement once again. So you can see that this diode VI curve tilted. In the next example, we're gonna measure the diode leakage in reverse direction. At the first step, we need to connect the diode in the reverse direction. So the anode goes to the SMU3 and cathode goes to SMU1. We will start from the default screen for the diode measurement. Then we press next, and start-stop limits should be equal to your diode maximum reverse voltage according to datasheet. So here we will set 0 volts, and the stop value should be, let's say, well, our device has limits 40 volts, so we will set it here. The step should be about 0.1 volt. So the step should be not more than 200 number of steps. So let's set it to 0.5 volts. Okay, compliance current and distance should be equal to your maximum expected leakage current, and let's imagine we do not know that, so let's say something like 10 microamps, just an example. Okay, then we will change nothing in the zero potentials SMU3. Press next. And here we should repeat the same settings from the previous page. So 0, 40, 0, and 10 microamps. Okay, press next. And press the single measurement, and we can see that there is actually nothing that's drawn on the graph almost, because our scale is too large, so we need to adjust our settings. Let's press auto scale, and here we can see the actual values. So just an example, so this way we know that our current, our reverse leakage current, peaks out at about 15 nanoamps at 40 volts. So what we will do, we'll go next. And set our current limit to 20 microamps. Sorry, to 20 nanoamps. Press next and do the same change for the y-axis, the current. 20 amps. Go next and do single measurement. And here finally we can see clearly that our leakage is actually starting around, well, about 2 nanoamps. Then we can press extended marker and use our knob to actually investigate which leakage we have. So around 10 volts we will have 10 nanoamps of current leakage in reverse direction, which is quite good. So for our test we will use this BC557C transistor. This is PNP type, and we will connect this in following way. The emitter goes to SMU1, base to SMU2, and the collector to the SMU3. So the next thing that we should do is to open this transistor datasheet, and from that datasheet we need to know two numbers. The first number is collector voltage and second number is collector current. So by the look in the datasheet we know that the collector voltage for this transistor is 45 volts and the collector current is 100 milliamperes. So let's remember those two numbers. After we connected our transistor we need to press channel definitions, and we will use the pre-configured settings for the bipolar transistor. Then we need to press next, and here you configure your collector voltage. So we know that from datasheet it is 45 volts, more precisely minus 45 volts. So we will set it like that. So the start is 0, and here we will set minus, to be safe, minus 25 volts. Okay, we will use logarithmic scale because it's much more better and illustrative than the linear one. So we'll switch to the log 10, and 44 steps is enough. The current limit is, well, let's say the same 100 milliampere, just not to burn our transistor, because we know that the current limit is 100 milliampere from the datasheet. Then we will move to the base current settings, and for this usually the 5 values is enough, so the SMU will just switch the base voltage 5 times. So for such transistor the base current usually is 1% from the collector current. So if we know that our collector current is 100 milliamp, so the base current should be around 1 milliampere. So let's change it from 0 with minus 20 microampere steps. So this will give us 1 milliampere in total. The compliance voltage is, let's say, minus 1 volts. So we are not changing anything else, and we press next. On this page you will define the graph limits. So I suggest you to set this the same values as in previous page. For the emitter voltage we know that our limit is minus 25, so we'll set it like this, minus 25. For the collector current we know from the datasheet that its limit is minus 100 milliampere. And that's it. We press next and we press single measurements. Here you have your volt ampere characteristic of your PNP transistor. We can auto scale to see it better. So how to calculate DC current gain for this transistor? Well, you just need to divide collector current by the base current. So we know that our collector current is plotted on this axis, and the base current is basically presented in the steps, which can be visible here. So then we can call extended menu, press mark, and then just scroll like this. So this is our 0. You can see this dot is moving. This is our 0 base current. The next one is, so this is minus 20 microampere base current. So let's move it here somewhere. So right now we know that for the minus 12 collector emitter voltage and minus 20 microampere base current, the collector current is minus 8 milliampere. So then we just divide minus 8 milliampere by minus 20 microampere, and we will get value of 400. So this 400 is our DC current gain for this transistor, which is well within spec of the datasheet. We can do the same measurements for different base current values. For example, for this value we have minus 33 milliampere for the collector current. So for the minus 33 milliampere collector current and minus 80 microampere base current, we will have roughly the same DC gain value, which is 417. We just divided this one by value of each of these steps, starting from the 0. And that's it. This is how you measure bipolar PNP transistor with HP4145A. Thank you for watching.